Okay, so welcome everyone. Today, the goal is to start this new topic of multi-agent reinforcement learning. And there is this textbook written by this group of authors, and they have provided a website, a repository of slides, and a code base. And for most of this meeting, we will be looking at um, a mixture of the material, including the slides they have prepared. Now, this book builds upon all of the techniques in just ordinary reinforcement learning, which we had used this textbook to cover, the Sutton and Barto book. And it's also the subject of all of the previous recordings. So the goal in looking at this new book is to really focus on the multi-agent part of the problem. So even though there are chapters in this book that cover basic reinforcement learning, I'm going to skip over most or all of that material because we've already covered it, and I think it's covered in a more thorough manner anyway in the Sutton and Barto book. So it's more just useful for to have a refresher. But if it's okay with everyone, this for the purpose of going through this new textbook, we're really just going to focus on material that's new, and we'll make reference to the old material, but we won't dwell on it too much. So there are also these YouTube videos of this summer session they did. So there's 4 of them. These links you can find on the textbook website link, which is, and there's also, yeah, these are the GitHub repository links. But yeah, this is the main textbook website, and it contains all these other, yeah, these other links in it for now. Yeah, I'll, yeah, leave this up for a second. So I suggest, like, if you don't feel comfortable with the other reinforcement learning material, it would be good to review it however you want, either through the notes or the previous meetings that we've done. But yeah, if anyone does have a question about that as we're going through this introductory material, I can certainly try to answer those questions too. Okay, so yeah, this is the book, the small book. At least this is the PDF of it. You can look at the table of contents for a second and see. So for today, I was planning on just going through the introduction, which introduces sort of the multi-agent problem and all the terminology, and then some of chapter 3, where it introduces the more formal mathematical definitions of these things, and also makes the connections to game theory. This is a very brief overview of tabular reinforcement learning. And this, you could certainly look at it as an overview, but I'd recommend probably looking at the Sutton and Barto book for a lot of this material, because it's covered a little more thoroughly, and there's also like exercises and things that you can use to check your understanding of it. And I also have, let me see. So I did go through the textbook and highlight some things. So I'll try to refer back to this a little bit as well while we're going through the slides. Um, yeah, but I think we will use the slides, which are derived just from this book, for a lot of the introduction. So with that in mind, yeah. Okay, again, this is the book, pretty recent publication. So especially in part 2 of the book, there is a lot of, very up-to-date material, including, stuff using neural networks and modern architectures for that. But it's going to be a little while before we get to that stuff. Part 1 of the book is really focused on just defining these things and explaining how the multi-agent problem differs from the single agent problem and what kinds of complications arise. And that's also what we're going to focus on today, and just yeah, defining the problem. So the main difference, obviously, between moral and ordinary reinforcement learning is just that there is more than one agent, and the policy that actions taken by multiple agents. And there's lots of different problem classes that we could have. Like the agents could be competing with each other or cooperating with each other. And there are cases where the multi-agent problem is actually just a different way of breaking down a single agent problem, um, where the use of Marl would really just be a matter of convenience or maybe to make it computationally easier. But then there are these other cases where it really is a fundamentally different problem. And the types of policies you learn would be completely different than anything you could achieve with a single agent system. And those are the more interesting cases and the things that will sometimes involve significant challenges and even having a solution become possible. So, but the basic goal is we want to understand how multiple agents can act optimally. And this notion of optimal policy also becomes significantly more complicated with multi agents than with single agent. In fact, there isn't even really a clear definition of what optimal means in a lot of cases. And you have to add more constraints to the problem before you can even determine what this optimal behavior would even be. So, the book in the introduction, it does like briefly touch on different applications, but I'd say their discussion of it is like pretty vague and not that useful. There is one example they touch on in particular that I'll probably spend a little more time looking at um than but these different examples are sort of like the driving example is a case where you have like this partially observable environment. There's like the agents can't necessarily see everything that's happening around them. Whereas like this robot example is one where you have cooperation and these robots probably, do have access to the information about every other robot in the warehouse. And this would be a case of a problem that doesn't necessarily have to be solved in a multi-agent structure. Like you could consider this as a case where you have one system which is trying to control all of these things in a cooperative manner. But as is explained a little bit later, there might be reasons why you'd want to handle it as a multi-agent problem, because mostly because of the action space and how that can become intractably large if you don't split this problem up. But we've seen a lot of the recent success in Marl has been in like training these competitive agents to play computer games like this and achieve superhuman performance in some cases. So if we compare this to like ordinary reinforcement learning, there's a lot of things that are the same. And what the environment is this thing which has a state which the agents can see and keep track of. And then the state is influenced by the agent's behavior in the environment. This is the same as in ordinary reinforcement learning. But the main difference is that, like I already said, the agents, now there's going to be more than one agent operating in the environment, and therefore, you know, a different sort of looking action space. But we'll see that, each, like the environment state in general will be something that, I mean, in the most broad case of moral, I guess what's being drawn here is that this is showing like the full problem we will eventually build up to with all of its complexity. And you can see here that you have this environment where, let's say, like this entire rectangle represents the state of the environment. And then each agent here is only seeing this little circle, which is an observation. So in the most general form of the problem, the agents actually can't see the whole environment. They can see some observation of it, which, here it's shown as sort of like a limited horizon, but the observation function could be a lot of different things. Like it could mask out information in different ways, or it could allow the agents to see the entire environment, but maybe not see all of the information about the actions of the other agents, which is also a form of information which is lacking. But the environment itself is something where this state will in general change as a result of actions from any of the agents. And then there is this other note that, for the full problem, we would also like the ability for the agents to communicate with each other. I think this is not touched on that thoroughly in the book, but it is something interesting to keep note of where when agents communicate, the difference between communicating and taking an action is you can think of communication as an action that doesn't affect the environment. So it's an action that could send information to other agents, but what would distinguish it, because like obviously agents can communicate with each other through their actions as well. Like you can signal to other agents what's happening through an action, but the problem is your actions in general will affect the environment. So like let's say if you want to signal to other agents without necessarily affecting the environment, that's where this discussion of communication would come in. But it's an interesting thing to think about, but I think it does make the problem a lot more complicated. You also have to define like what type of communication is possible. Like the simplest case is you have like a finite set of messages that the agent can choose what to send. But in general, it could just be a generic stream of bits that could be sent out into the world, and that becomes a lot more complicated to train for.
We saying that like an agent would have a conscious decision to either pick an action or to communicate, or would it
Yes.
possibly do both at the same time?
You can set up the problem where on every step it can choose an action and a communication action, if you like. Like you could partition the action space into two things, and it could, I mean, it really comes down to how you define the environment. Yes, it could do both simultaneously. It could have the option to do both. And of course, oftentimes in the environment, you can have in the action space and the communication space like a no-op action
Okay,
where
makes
it
sense.
would select it, but it wouldn't actually do anything. Okay, let's see. Oh yeah, so here's one of the examples. Here actually, let me just pull up also this my oh yeah, a copy of that. I just want to see if out of my notes for the actual textbook, if there was anything I wanted to bring up and highlight. Um, oh yeah, obviously, like just like in ordinary reinforcement learning, you have to define the goals, which is really comes down to this reward function that the environment gives. And the one thing, a lot of this stuff could be anything like the state space, the action space. These could be very abstract things. But just like in regular reinforcement learning, the reward function it's a scalar quantity, right? Like that is how like so when we define these problems, the one thing we really have to make sure of is that we structure the problem so that the agents get this scalar reward, which is just a single number, and everything we need to define about the goal of the environment has to be contained within this scalar value. So then the example that they actually use in this slide is this level-based foraging example. Maybe if I show the slide for this, it's a little hard to tell what's going on here, but you basically have this seems to be an example in Marl, which is sort of akin to the grid world problem that we usually have in ordinary single agent reinforcement. So like in a grid world, we have this grid of discrete states, and then there's some goal state, and there might be walls or obstacles or things that the agent is trying to reach. Right. So this is a grid world where we have multiple agents, which are represented by these little, humanoid cartoons. And then there are these objects in the environment. And the objects, like an agent can move. So this is the action space. So they have the four directions, and then there's this collection action, and there's a no-op action, which is just the agent doesn't move. And the idea is for the agents to collect these items, and then, but there's constraints on how they can collect items. So like this agent has a level of 1, which means that it on its own could collect any of these apples that are labeled 1. But like these two agents now are next to this apple, which has a 3 label, because they can collect it sort of as a team as long as they are touching it and the sum of their level is greater than or equal to the apple, right? So now this problem could be structured in a lot of different ways, right? Like in terms of the goal. So you could set this up as a competitive game where the agents try to get the most reward for themselves and they ignore the other agents. Or it could be a cooperative game where the goal is to collect the apples as quickly as possible and the agents can work together to do that. And it could also be set up as a common reward game where the agents, like, all the rewards are the same, but it's not necessarily cooperative. And we'll see later some examples of how these games are defined, but they're often defined in that how the rewards are structured for the different agents simultaneously. So and this example is something we'll come back to later when we actually have some of the solution algorithms and see how to set up the problem and what the performance is like. But this is the general diagram for a model system. And if you compare this to the normal reinforcement learning diagram where you just have one agent, you have the observation and reward, and then the environment and the action. And here, the only difference is that if we stack up all these n agents, like the reward signal is something the environment has to provide. The observation could be a full observation of the environment, but in general, it's going to be some function of the environment state, which is limited somehow. Limited in terms of both how much of the environment it can see, but also how much of the behavior of other agents it can see. And the way most of the problems were structured in the book is that one step consists of every agent like being allowed to take an action. So we have to wait until every agent takes its action. And then all of those actions are concatenated together into this joint action, which then the environment uses to update the state. So it's only until like the way these environments are defined, um, right? The environment can only like advance a step once it sees the action of all of the agents that are present. And we'll see this notation come up a lot later, but this joint action notation. Um, yeah. And then, like the new environment state would be updated. And then whatever the observation function is, I mean, this observation function, you should think of it also as part of the environment, not part of the agent, because it's like the agents are the things that are limited. Like they can't see everything. So it's like the environment sort of knows, I guess, for each agent, what set of information, but it's sort of this observation is a bit of a combination between the agent and the environment. You could think of it as like if the agent was some kind of robot with sensors, the observation would come from the sensors. And you can think of sort of like the sensors and the environment, the sensors as part of the environment. I mean, often when we talk about robots and things like that, the sensors and the wheels and like the control mechanisms of the robot are actually usually part of the environment, whereas the agent is really just the thing inside the robot, which is collecting the data and then making the decisions. Which is really the only place where like sort of the brains of the robot doesn't really have control over the limitations of the sensors and the limitations over the actions the robot can take. So yeah, that's sort of usually how problems are defined in reinforcement learning. Yeah. So then if we go back to this like foraging example, like the point that's made in the book is that what makes the multi-agent system somewhat complicated is the fact that the agents have to figure out how to either coordinate with each other or compete against each other for whatever the goal is. And we'll see that if they're coordinating with each other, that is a little bit easier of a problem because we can think of that. If you look at this, if our goal, like if this is a problem where we just care about the net performance of all the agents together, like in the collecting example, we just want them to be as successful as possible collecting these apples. Even though we have these n agents, we can actually take this whole system and collapse it into a single agent that actually controls all the n agents and then decides what joint action to take. right? Because that would be equivalent to a single agent reinforcement learning problem where we're trying to maximize the return because the return we care about is the sum of the returns of all of the n agents. Now, one of the reasons why that may be challenging for this problem, although you could experiment with that and test this directly, is that this joint action space is going to get pretty big, right? So each agent in this problem has 6 actions. Now, the joint action space could be, is going to be 6 to the n in size. And it's possible that the single agent algorithm we try to use just won't be able to cope with an action space that big. It depends on the problem. But, usually when we think of the complexity of these problems, we have the state space and the action space. And for some cases, we care about the state action space as a joint thing where there's a tuple of a state and an action, in this case, a joint action. And this is going to grow, exponentially with the number of agents, the joint action. And that's going to be multiplied by the state space as well. And we would also have to augment the state space with the information about the position of all of the other agents, which is also going to grow exponentially. So we have a bit of a scaling problem with trying to handle this as a centralized control problem. And that's one of the reasons why you would consider a multi-agent algorithm. And I think that might be discussed here. So yeah, what I just said is decomposing large problems. This is growing exponentially, 6 actions. So we already have 216 actions for 3 robots. Now, this is probably okay. Like this size of an action space is not going to break a lot of algorithms. We could manage it. But, with Marl, each individual agent only has to consider 6 actions. So the problem could be more tractable, but then we also have to deal with the complexity of the problems we can have when trying to train, a Marl system to begin with. And then the other case, which is probably a better reason to use Marl, is when we have a problem where the decision making is inherently decentralized. Like you have agents where they're unable to see relevant information from all the other agents, like autonomous driving, where you have cars on the road and they can only see a limited set of information around them. You can't guarantee that they know all the information about the environment and the other agents. So each one really needs its own independent policy that it can use. And also, competitive examples is another case where it doesn't really make sense as a single agent RL problem. However, there are drawbacks to using this technique. We lose a lot of guarantees and assumptions that are necessary to make conventional RL problems work. And one of them is that as this thing is learning with multiple agents, right, we have non-stationary distributions of the environment because the environment's affected by the actions of other agents. Those are during the training process, especially, can be changing over time. And, we're trying to make observations and take averages and learn, but we're dealing with non-stationary distributions. So that is a problem. Also defining what's optimal. We'll see this later when we talk a little bit about game theory, but we may need to make arbitrary choices about what type of solution we want. It won't be entirely obvious, what the solution even should be when we look at a multi-agent system. Then there is this issue. Oh yeah, so scaling. I mean, this scaling of the number of agents, this I would say, this isn't like a new problem introduced by multi-agent learning. This is a problem in single agent RL as well, because if we do try to add a lot of agents, right, we still have the scaling problem in the action space, right, which is going to grow exponentially, even if we wanted to use a single agent problem. But then, credit assignment is already a problem in reinforcement learning when we have these long time horizons between reward and action selection. And when we have multiple agents, not only do we have potentially a long time horizon, but we also have confusion about which of the other agents are responsible for what's happening. I mean, even if we can observe a full action history of what other agents have done, we would we don't have like a full environment model. We don't understand exactly how the environment would change over a long period of time as a result of the actions of multiple agents. So it becomes a lot harder to tell which information about the past is actually a reason why an agent got a particular reward. So let me see. It looks like someone wrote something in the chat. Let me just see if I have to address this. Uh, yeah. So like usually, I mean, this is true of normal ordinary reinforcement learning too, is we usually think of it as a discrete step time problem where we're looking at individual steps. You can extend some of this to continuous time, but a lot of things get messy. I mean, here we're also looking at discrete actions. We also would, when we talked about single agent learning, we look somewhat at continuous actions, which is also possible. Continuous states are a little more straightforward. That is more common where, yeah, the state space could, like you can imagine easily like the position of something could be a continuous value instead of a position on a grid. So that is commonly done. But yeah, turning it into continuous time is a lot more complicated. It introduces a lot of other problems, and often it's not that necessary because even if we're controlling a system, there often is some natural time scale over which we're making decisions. Like if you have a control loop, it's going to run on some interval. So you can always think of these as breaking them down into discrete time steps, even if those steps are very short. Because yeah, I mean, you can always like look at the limit of the discrete time problem as it goes to very, very short time steps, but the theory and technique should still work the same way. You just make the time step smaller. But that does have a scaling problem because then you need way more time steps, to cover a reasonable period of time. But are there any other questions about what we've gone over so far? Uh, just gonna I think the slides might kind of skip over this, but yeah. In the book, there is this discussion about like different ways you can structure the rewards, and they do refer back to this level-based foraging example. Um, so if there's a shared goal, like the agents could all receive a reward together if one of the items is collected. But you can also do a competitive. Oh yeah, well they also use like a case where the agents only get a reward when they collect an item, but the agents not involved don't get anything. A more common example of a competitive game is just like a two-player game where the player that wins gets a reward of 1 and the loser gets -1, and there's 0 for draw. So like these types of games are what we would call zero-sum games. But the origin of that name is just from the fact that any outcome, if you look at the rewards for all the agents involved, the sum of that is always 0 in a zero-sum game. But that is like the most common and simple competitive game scenario. But we can also mix these two things up. Like the common reward case is every agent gets the same reward for a success. You have the zero-sum scenario. But there's also a more general example where the agents can just get arbitrary rewards. It doesn't necessarily sum to 0 or anything. And then, the actual behavior you get, like the type of solution you get, will depend on defining other things. But yeah, that we'll get into more when we cover chapter 4 about what type of equilibrium we actually reach when we solve a game, because we'll see that this actually isn't a unique solution, unlike in single agent reinforcement learning, where when we discuss optimal behavior, there actually is a single unique, well, at least a unique value function that there's a class of solutions that all achieve the same optimal reward. And that is not necessarily the case when we have a multi-agent problem like this. As we talked about the joint action, decomposing the problem. Oh yeah, and then there's just these different discussions. So when we discuss one of these moral problems, there are different, these are just the important qualities of the problem. And a lot of these are pretty obvious. We have like the size of the problem. Typically, we have the state space and the action space, but now we have the added dimension of the number of agents. Then for the knowledge part of it, there's a lot of options, right? The agents could have full information about the environment and the other agents. And when we talk about observations, we can then restrict that information in all kinds of ways, down to them, only knowing very limited information about the environment. Then for the reward function, we have to decide if the agents are competing or cooperating or doing some combination of the two. And then, the actual equilibrium that the agents find is going to depend on some other constraint that we've put on the problem that we'll discuss later. And then we talked about, if the agents can coordinate, if we're thinking about it like there's a central agent controlling everything, or if the agents have to communicate information with each other in order to achieve that kind of coordination. So then we got these examples, the robot. Okay, so I already mentioned how the zero-sum game works. That's just a situation where the sum of both agents, whenever they get a reward, is always 0. But this is this competitive play example, which is probably the example people are most familiar with these multi-agent systems, how they've been used, is, doing some kind of self-play set up in a zero-sum game reward. But that is a simpler case of moral where there are some guarantees. Oh yeah, okay. So we already covered in the slides these challenges, right? The non-stationarity. But really, like, the biggest difference in moral and the biggest challenge is this notion of optimality. Because, right, like when we talk about single agent reinforcement learning, we have this result that a policy is optimal if it achieves a maximum expected return in each state. And we know for these Markov decision process problems that this solution exists and it's actually unique. So if we find this type of equilibrium where we have, it's not exactly an equilibrium. This is like a fixed point of the value of the Bellman operator in the value function, then we have this optimal return. And then all the optimal policies will have the same optimal return. And it is intuitively what we want, right? It is the policy that achieves the goal most successfully. And we have a clear meaning of that. But in a multi-agent system, each agent is distinct. And just because one agent achieves a high reward doesn't mean the others will. And they could also sabotage each other, or they could be cooperating with each other. And instead of having a single optimal policy, what we're going to have instead are different equilibriums that can be achieved between the agents. But that equilibrium might not be stable. It could change. It could evolve differently during the learning process. And as a practitioner that's trying to define one of these problems, we actually have to decide ahead of time what kind of equilibrium we care about. And, the goal of the equilibrium could be some kind of fairness condition. It can be a stability condition, but the challenge is both, picking what equilibrium condition actually makes sense for the problem. And then can we actually have a learning algorithm that successfully achieves that equilibrium? Because it might be hard to even control what equilibrium is reached. So that's really the new, like the biggest single thing which becomes a challenge for this. Um, yeah, and then yeah, we this multi-agent credit assignment thing is, really it's related to this non-stationary problem, but it's hard to disentangle, which agent was responsible for this. And what is brought up later in the book is that actually when we define these multi-agent algorithms, we usually want to give the agents access to the history of actions from the other agents, as well as the state history. And this is something which is not necessary in a single agent RL because of the Markov property of the environment, right? Because the agent is now interacting in an environment with other agents, from the single agent's perspective, we've lost this Markov property. So now we talked before in RL how to restore it. One way to restore it is to provide this history of the previous actions, but like it's a lot of information, right? Because we have to provide the history of all the previous states of the environment and all the actions taken by the other agents. And in general, it's going to be some function of that where we might have to not have all that information, but have to summarize it somehow or have an incomplete copy of that information. And then the agents are going to have to learn how to incorporate all of that information as well as the current state information to decide what action to take. But yeah, it does introduce a lot of other complexity. Um oh yeah, and I guess this is an example of, yeah, two agents converging to something, but again, like this policy is, this convergence might just be to a particular equilibrium, but not necessarily the one we want. That has to be controlled through other means. Yeah, the credit assignment thing we already talked about. Okay, actually, let me go back to this and just say, to wrap up, this is just, this introductory chapter. There is finally this discussion of, what is the purpose of doing all this? Like, what are we trying to achieve when we study multi-agent reinforcement learning? And the book has a particular focus, but the authors have, pointed out different options for what the point might be. So the main focus of the book is this computational focus. The computational focus is, how can we compute solutions to competitive or cooperative games that are like good solutions. So in a competitive game, it might be, something which is good at competing with other agents, even other agents trained with other techniques or actual people. And then in a cooperative scenario, it would be, achieving the highest reward for the combined behavior of all of the agents. And in this scenario, the goal is to really develop algorithms that are competitive with other techniques. And like if you look at other ways of figuring out um, optimal behavior in a competitive two-player game or in a coordination problem, to see that to develop algorithms that find these solutions, effectively. Now, there's this other case which is also discussed in the book, and this is really more about how the learning process goes. So like when we conduct a learning algorithm, we think of it as like we don't just care about the end result and then deploying that agent, but the learning process itself might be part of the product that we're trying to create. Like we would like to make sure that the behavior of the agents during the learning process follows some constraints, does well, is directed towards a particular equilibrium. And then you could have some other static algorithm from some other technique that gets you some result, but we would want to use a multi-agent reinforcement learning technique because we care about actually how the agents behave during the learning process. And there is some discussion of that in the book. The most focus on this is actually on um, putting constraints like here's an example here of, making sure that the performance of an agent doesn't drop below a certain value while it's learning. And that could be important in some real life scenario of this. But for this type of thing, the behavior during learning is more important than the actual like end result or what it converges to. We don't care about this more like computational theoretical result of like what are the different equilibrium, right? We care more about the non-equilibrium behavior or how the agents behave as they're actually changing over time in response to each other. Then there's this other use case, which is not really the focus of this book, but it may be interesting for other people. And I guess if you have the techniques in this book, you would be able to do this kind of research. But this is to use multi-agent learning as a way to make an analog to the real world and see like how multiple parties would behave in a certain environment. And in that case, the goal would be for the agents to actually interact with each other in a realistic way so that we can use it as like a testing ground to study things. And this you could imagine this being used in economics or in biology where you want to see different plausible examples of how multiple agents, whether they're animals or people, would interact with each other given certain constraints on what their goals are. And then yeah, I guess those are the three main areas. The book, as I said, is more focused on optimizing decision problems, finding more like we do in single agent RL, where we do try to find an optimal policy, the meaning of which is more complicated in the multi-agent problem. But, you know, we will touch a little bit on some of these other approaches. I think in particular the prescriptive approach is interesting, especially when you're looking at how groups of agents actually arrive at an equilibrium. Because just because an equilibrium exists, like doesn't mean that the system can actually get there from a given starting point. And that will become more clear as we get more into the material. But it is pretty relevant when you're talking about groups of agents to understand, both what the optimal equilibrium solutions are, but also what is the process actually like of getting there and how and it may never get there, in which case we actually do care more about the learning process behavior than the actual solution. Whereas in single agent RL, we really usually only care about like the final optimal policy, which is what we're trying to find in the first place. So yeah, for the rest of the book, so we will look next a little bit at chapter 3, which involves defining game models and some of the important concepts that really distinguish moral from ordinary reinforcement learning. And then as we go on, this is just sort of a high level overview of what the book's going to cover. But in chapter 4, we get into more of how we define optimal behavior in the case of multiple agents. And then there's some material which ends up repeating background information from reinforcement learning. But really, it's then chapter 9 where we get into the more recent algorithms that are actually used in practice in trying to solve these problems. So, we'll see how long it takes for us to actually get there. But we'll definitely spend a lot more time on chapter 4 will be the big, like, a lot of the foundational game theory information that we'll need before moving on. Okay, so that pretty much covers chapter 1. And then yeah, so again, chapter 2 and the remainder of these slides here is covering information from basic reinforcement learning. This is the stuff that I'm not going to go over now. There's lots of information in videos where we've gone over this stuff in the past. Yeah, this is this diagram I mentioned, with basically right out of the Sutton and Barto book, right, of this single agent interaction, and we can compare this to the multi-agent version of the diagram we had before. But before I move on to chapter 3, which is our first actual like legitimate step into the multi-agent problem and defining it in more detail. Are there any questions about the introduction and just these different issues that come up with multi-agent problems, the comparison to single agent? I'm just going to pull up my notes for chapter 3. Okay, so I guess let's see how far we get touching on this stuff. Yeah, like I said, there are no exercises in this book. So we'll see what might be some we have to come up with ourselves as interesting things. The only exercises that occur later on are more programming exercises that are part of this summer workshop. And I think that really heavily uses their code base that they've developed. And I don't know how, I think it's more of like sort of a tutorial workshop thing. It's not really about the theory or the mathematics of it. But, we'll see. Maybe there's some things I could bring up that might be interesting things to think about. But the book kind of leaves that to us to worry about. But for this chapter, um, the main thing we're going to focus on is this section on game models. And this is where we define sort of the formal structure of the multi-agent problem, which is going to sort of use game theory as a basis and then sort of combine it with the Markov decision process framework. And then we're going to arrive at this, finally, the end point of this is defining these partially observable stochastic games as the full moral problem that we're concerned with solving. But, it's helpful to look more at the theory of simple cases and then build up to it slowly. So, game models. So, here's this diagram. Actually, I took this diagram. I did add one little thing to it. So, we're not going to talk about in this chapter solving these games. The purpose of this right now is just to actually define the games themselves and what they mean. And then chapter 4 is going to deal with actually different solution techniques and what we even mean by that. Okay, actually, probably have to zoom. Sorry, this is probably too small to actually see. This is a diagram from the book. This is helpful to see how these things connect. So this purple circle here, Markov decision processes, this is the entirety of what we were concerned with ordinary reinforcement learning. We have a single agent, which makes decisions in the environment, and then the M states are what make it a Markov decision process, which is there are different states, the actions affect the states, and it has the Markov property where all the transitions only depend on the current state we're in and the action the agent takes. What I've written here in a small font, which I can't really easily zoom in on, is the K-armed bandit problem. Now, this is in the Sutton and Barto book, if you recall. Before we actually tackle the reinforcement learning problem, we cover this chapter. And the purpose of this chapter is to have a toy problem, which is simple enough to learn some things, about these techniques. But if you compare it to this diagram, right, this is one agent M states. The bandit problem is one state, one agent, right? So I guess it's like the missing piece from this diagram, right? We have one agent M states. The bandit problem was one agent, one state, in which case the only thing we're worried about is the action selection. But the situation we're in is always the same. Um, Here, these are written as sort of parallel things, but the first example of we're going to expand this a little bit. The reason why this is drawn parallel to this and not above it is because in some ways this is a step backwards from the Markov decision process, right? We have n agents, but only one state. So actually, this is sort of a mixture of this and the bandit problem. But because the bandit problem was the first problem we had, which is a single state problem, and it's sort of the same as this normal form game formula. It's just that now there's more than one agent involved. But at every step where the agents are interacting with each other, the interaction is the same, right? Like they know based on the actions of other agents what the rewards are going to be, as part of how the game is designed. So again, and this says repeated normal form game. Yeah. So then we have a little bit above that stochastic game. Now, what makes it a stochastic game is we turn it sort of back into a Markov process where now we have multiple states. So the agents can see, but now as the agents interact with each other, the environment itself will change, just like we have with a Markov decision process. And then this, compared to a stochastic game, really the only difference is now that it's partially observed. Like the agents don't actually have full information. But right, this is like the superset of everything. So even like this, you can treat as a subset of this, right? This where we set n to 1, and then we have states that are fully observed here. Or actually, this could be partially observed as well, but it's not, usually with these, it's a fully observable state. Yeah, actually the multi-arm bandit is written here. Yeah, so similar to how a multi-arm bandit is the basic kernel of the MDP. The normal form game is a basic building block of all games introduced in this chapter. Although, so they do mention it here. I don't know why they didn't put the bandit like into this diagram. It does seem to fit pretty well. But nonetheless, this is what we have. And for a normal form game, which actually isn't even on here, right? This says repeated note. So we talk about a normal form game without repetition. We're really just talking about a single interaction between multiple agents, right? So we have a set from 1 to n agents, and then for each agent, they have a finite set of actions they can take. And then there's a reward function, which takes the joint action and then produces a vector of rewards where there is a unique reward for each agent. I mean, it could be the same reward, but it has to produce a reward for each agent. So then even though this R sub I, right, is a separate value for each agent, it depends on the actions of all of the agents, right? Which is why these agents are actually interacting with each other. Even though the game is not repeated, it's just a single like interaction. You could think of it like rock, paper, scissors as an example of a game, which is like a single interaction if we don't repeat it. But the outcome of the game does depend on considering all of the actions as a whole. Let's see. Back to this slide deck. Yep. So here's what I just said. So this is the definition of the normal form game, not repeated, right? Here's the reward function. There are no time steps or states, right? We're just considering the game as a single interaction. So what happens is each agent samples an action from its policy. Now, we're considering right here, like this pi sub I, the I refers to the agent in question. So we're, these agents are like, before we sit down to play the game, the agents, are defined by some policy here. The policy defines the probability of the action selection. And then together it forms a joint action between all the agents. And then there's a reward which acts on the joint action. Even though this is just a lowercase a, right? It does consist of all of the actions. Now, right, the game is defined on the relationship between the reward function. So in a zero-sum game, regardless of what the action, the joint action is, the sum of the reward output is always zero, right? So an example of this would be like a game where one player wins, the other player loses. That's always the outcome. And then the reward structure would be like 1 and -1. And that would produce a reward of 0 in all of the different cases. I mean, there's only 2 cases for that, right? It's either 1, -1, or -1, 1. But you could also have more elaborate zero-sum games as long as this is true. In common reward games, the reward is the same, right? So this means that regardless of if we compare any 2 agents on a particular, actually, I guess this should say for a given, joint action, then the reward is the same, right? This is like for a particular case of this, where R does depend on the joint action. It's not written here. It doesn't mean they all receive the same reward, like regardless of the actions. That would be a trivial game where nothing matters. So it's just that does zero-sum game assume winners and losers? Well, when we talk about these games, we don't actually talk about winners and losers. We instead talk about the reward function. So usually if a player receives a reward of 1, another player receives a reward of -1, then we would classify one as the winner and one as the loser, sort of colloquially. But you could also have a zero-sum game where both agents get a reward of 0, in which case that's more like a draw scenario. So it doesn't necessarily have winners and losers. You could have even a 10 agent game where 2 of the agents are like, there's one winner, one clear loser, and then all the others are draws. It's like the only property really it has to have is this sum of 0. But you could have scenarios of the outcome where it's 1, -1, and then other joint actions where it's like 0.1, -0.1, which would be like still a zero sum, but a more mild difference between the two. So that could be like, it doesn't necessarily have to be just a clear cut win loss. It just has to have this sum of 0. And then in general sum games, there is no restriction on the reward function. So the reward values could just be anything. Yeah, so here's some examples. Now, if we have 2 agents only, we can actually write the whole game out as this 2x2 table. So this table, each column in the table, each row and column represents one of the agents. I mean, the actions of the agents. So, you could think of like this is agent 1, this is agent 2, and then the size of the table depends on the size of the action space. So this is an example of a zero-sum game where there's 3 actions for each agent, and then what's shown in the table is the reward function of the joint action, right? So here, like the joint action is S, or both agents select scissors. And then for all of the cases where the joint action contains the same action for both agents, the reward is just 0 for both, which is a tie, but the reward sum is still 0. And then all these other cases are cases where there is one winner and one loser. And then it's, the sum is still 0, -1 + 1. This is an example of a common uh, common reward game, right? Where within a given joint action, the reward is the same. And that's why for this game, notice how there's only one number written. You only have to write one number here because the reward is the same, right? So we see that when the actions match, then the common reward is 10. And when the actions differ, like here, one agent selected A and the other selected B, and vice versa. In this case, the common reward is 0. And then the prisoner's dilemma is an example of a general sum game where we can see that in this case the reward sum is -2, but in this case it's -6, and in this case it's -5. So all of the different joint actions, have different reward sums. So, right, this is not a clear cut case like these are. Is there any questions about these normal game definitions? Right, that's what we said, right? These are normal form games. A 3-agent game could not be written as this kind of, this, then it would be like a 3D table, like because there would be another agent to worry about. But in general, like we could represent a normal form n-agent game as like a tensor table like this with just multiple dimensions, one dimension for each agent. Let me see. Oh yeah, okay. So it's labeled down there. So these are like we've introduced this where these are non-repeated games, right? The entire game is contained within this matrix here. But the reason why these games are interesting is because the reward values don't just depend on your action selection, right? They depend on the other agent's action as well. And you don't necessarily know the other agent's action ahead of time. So even a game as simple as this, there is the question of, what should, like, how would an agent behave given that it does have this information, it knows this matrix, but what it doesn't know is what the other agent is going to do. And this depends on the assumptions about if the other agent knows about your behavior, etc. But, in these cases, there are these equilibrium conditions. And, in the case of the prisoner's dilemma game, you can look at, for a given agent, like let's say that, this like agent knows that action D was selected, for example, right? So now, like, let's say agent 2, the rewards for agent 2 are the second number here, right? So you can get some idea of how these equilibrium conditions work by seeing, okay, actually in this case it's a simpler problem, but let's say that we assume that this agent 1 selected action D, right? You can see that for the first agent, if it wants to maximize its reward, then it has a choice of either -5 or -3. So -3 is better, select -3. Now let's look at the other case where we assume that the first agent selected this. Then it also has two choices, right? It could either get -1 or 0. And in this case, 0 is higher. So for this particular game, this happens to be an example where regardless of what the other agent does, it seems like action D is preferable to take, right? If we analyze the game from the perspective of, let's consider all the things that our opponent could do. And that's why in this case, this action D would be considered a dominant action because it happens to be better in both scenarios. Now, not all games will have this dominant action even. Like that's not necessarily true. We could have cases where different actions are more favorable depending on what our opponent does. This just happens to be a case that does have it's the same for both agents too. They both have the same dominant action, which means that the behavior, if they follow that, will end up being this. which of course is a worse outcome than this. But the problem with this outcome is that this is not a stable outcome. And the reason why we say like this is not stable, this is not an equilibrium scenario, is because let's say that the agents were behaving this way or did behave this way in the game. Or, we told agent C, hey, like this is what's going to happen. The agent, if it knows this, it can always switch its action to this and get a higher reward for itself. And that is a problem. I mean, it means at the very least, even if we prevent this agent from changing its actions, it does mean that this agent it should switch its action, right? Whereas if the agents are in this scenario and this agent is considering, well, maybe I should change my action. Like I know that this agent is selecting D. However, its other choice would produce a worse outcome for itself, right? It would go from -3 to -5. So that's why this combined action is actually, stable in the sense that if both agents consider whether it makes sense to change its behavior, they would decide not to change their behavior because the result would end up being worse. So does that make sense to people? Sort of analyzing when. I mean, this is just one way of analyzing games, but it's a common one, especially for the prisoner's dilemma. But yeah, also in this case, like remember, we're not repeating the game yet. So this is like these agents just know what the rules are and what the possibilities are for the other agent. But we're asking them like make a decision ahead of time without any additional information, right? So they don't know. It's a totally different problem when we consider that the agents can observe other agents' behavior over time, which we'll get into next. But that's the case of a repeated game. But yeah, any sort of a discussion of agents communicating would only occur in a repeated game scenario. So obviously, these games might have, be of limited interest to people in the non-repeated case, but this is just sort of a basic introduction to game theory. So, the first step forward into a more, what would be considered the first sort of real multi-agent problem is repeated normal form games. Still have one state, of course. Now, in this case, the state is actually like the game itself is like we are playing this game, we're just repeating it, but the game, like when we talk about the state in a multi-agent case like this, the state consists of the rules of the game as they exist, and the state of the game is not changing over time in this scenario. So, right, this table, just think of this as a two-agent normal form game. Now, depending on the action taken, so what's being shown here is an action of 2-1 was selected. So agent 1 selected action 2, agent 2 selected action 1, which is this part of the table, right? So given this joint action, this is the reward. It's 2 for both agents. And then we transition back into the same game, which we can then repeat, an infinite number of times, generally, is what we talk about. So this is a sequential interaction. The agents continue to sample. However, the policy now is conditioned on the history. And here the history is the joint action history. We could also consider limited history, but it's just a subset of this general case where this game is repeated, right? Every step of the game, there is this joint action information. And then we're going to allow the policy to still, be a particular policy for each agent, but this policy can be an arbitrary function of this history, which could continue to extend, right? That like this history is going to keep extending into the future for as long as we play the game. Yeah. So does this make sense to people as we're repeating? Now, unlike in ordinary reinforcement learning, right? We never condition the policy on the history of the action selection because that is not relevant in a reinforcement learning problem, or it shouldn't be relevant. But, does everyone see, or does it make sense to people why the history is important here? If we're thinking about like what information would actually be necessary to allow the agents to be successful. I mean, it has to do with the Markov nature of things, which we usually want when we're solving one of these problems. So, the actual evolution of this game does depend on the other agent, right? Like we don't know the other agent's behavior, and we don't know if that behavior is changing over time either. Like it could be a policy which is the same every time, but because the other agent exists in the problem, it creates a potentially, non-stationary process. We can't simply make observations of the game over time and learn anything because the other agent's behavior could be dependent on our choice of actions. So we really do have to include this information for the agents to be successful because now the other agents are sort of part of at least their environment, like from their perspective, and it's a problematic environment because it's a non-stationary one. So it's not even enough to, well, we'll get into this later, but you can't actually treat this like this type of scenario. You can't treat it as just a single agent problem where you have other agents because the other agents are changing over time, and yeah, that can cause problems. Okay, the next before we get into the stochastic game thing, let me just bring this up again. Um, yeah, okay. So I said, the entire history of joint actions is now the policy space, which is a very large space of things to look at. Also, usually when we talk about this, we consider infinite repetition. So the game is going to go on forever. If the game terminates in t time steps, that creates these end game scenarios where agents could it might be advantageous for them to change their behavior completely as the environment gets closer to terminating. If we do want to think about finite time steps, usually we reintroduce the discount rate to these problems, where you could think of this as discounting future rewards. The other equivalent way to think about it is that there's a probability of 1 minus gamma that the game will terminate. This is like creates a Poisson process of like the probability of when the game will terminate, or there's an expected value of the number of steps here, but there's an exponentially decaying or there's a like the probability of termination is not changing on every time step, but over time, the more time steps you have, the higher the expected value is that the game will have terminated. And of course, if the game is not repeated, we can just think of that as a case where there is just one repetition of the game, or one instance of the game. It's not repeated at all. But of course, we are interested in not just, repeating the same game, but actually dealing with this as a Markov process or some version of it with different states. And that's where we get into stochastic games, where now we have M states instead of the one state of a normal form game. But the reason why we introduced this already is because the states we're talking about, each individual state is just a normal form game. And that's what we're going to see here. So we have so far, everything is the same except for this state transition function. Now, this thing is going to take the current state, the joint action, and produce a new state. And this looks the same as in a normal Markov decision process, except now this action is the joint action. And the state is now one of these games, actually, rather than being like something like a position in the grid world or something. Like the state has to be a game which sort of contains the information about how the rewards work, right? In this case, the reward function now is a function of actually three different things, right? Including the joint action. I mean, usually we don't have to consider all three of these things for the reward function, but the reward function now is going to be state dependent. Another way of thinking about this is that we're transitioning to basically different games on every time step, where each one of those games has its own reward function. But we'll see that here in this table, right? So we had before the previous table where we had just one of these circles. And this circle, right, defines a two-player game, the joint actions. And here what's being shown is three different states where there's three different games. And then if this joint action is picked, so from the state, right, we can see that now this is the resulting reward function from this joint action selection. But in addition to that, we now have this transition, and it's not just a deterministic transition. This is now a stochastic transition where there's an 80% chance of ending up in this game state and a 20% chance of ending up in this game state. And really, like, to make this a complete diagram, you would have to also draw other arrows to show the transitions for the other joint actions here. Right here, there are each one of these states has four different joint actions, and each joint action in general will have a different transition. But when we draw these diagrams for a normal Markov decision process, right, we're just talking about single actions and then a single reward, and then we'll draw all the transitions to the other states, right? But here, each one of these states is one of these matrix games. And of course, if we had a zero-sum stochastic game, it would just mean that every one of these game states we could end up in would just be a zero-sum normal form game. But, in the general case, we could have mixtures of different types of games we end up in with different transitions. And the other difference we have is now, we're in a state, again, like the policies are now conditioned on the history, on this full history up to the current time step. And they select an action from this distribution. But now the history is not just the joint action history. It is also the state history. It contains both. So, the state action history. And this is important, right? Because we can't really judge the meaning of the actions unless we know what state we were in when those actions were taken. What we assume also is that the agents also know what, like, the meaning of these different states, like how the rules of the game work. But there's cases where they don't have that information. But when we have this fully observable situation, like the agents could know sort of all the potential rules of the game at every state in the problem. Like this would be known when we have the tabular, like the fully observable tabular case of the problem. That's a case where all of this information is known to every agent. What's not known necessarily is what the policies are of the other agents. That's something that will have to be, learned over time. So we have the state action history. The transition function will, right, produce a transition to the next state given the current state and the current joint action. And then there's the reward function, which now depends on the current state action pair, as well as the transition state. Right, this is because you could have games where, given the same state action pair, there are different reward outcomes that may depend on the state it ends up in. Sometimes this is not true and it only depends on this, and that might make the problem simpler. But in the most general case, it can depend on all three of these things. And then, we could have either this could go on indefinitely or have a terminal state. A terminal state could be like, a game state. Like this is an example here where, right, there's no terminal state. Right, these always transition somewhere, but a terminal state would just be a case where the game is over. Like there's no further activity to worry about. Yeah. So the foraging example is a case of this stochastic, or sorry, not stochastic game process where we can think of the reward function, right, is depending on where all the agents are in the thing and what their actions are, right? Like if the agents are all away from the apples, then obviously like there's no reward possible for that outcome. But we could define it, in different reward settings where we have common reward, or, here's a case where, you only give a reward to the agents that receive an apple. Okay, so yeah, the basic addition here is just the existence of multiple states. The final iteration of this, like the full problem, the partially observable problem, is a case where now, on top of everything we've already introduced, the agents get incomplete information about the history, right? So this is like the states and actions of other agents. They may, like this diagram isn't really any different, except that these sort of dotted circles represent the incomplete information. But now the observation function will take, right, what actually happens, like, well, it'll basically produce the probability of observing something from the state action pair that was seen in the environment. And on top of this, the policy now, in this case, right, an agent receives an observation, which is given by some function which tells you how do you translate the actual information from the environment into the limited information that an agent has as an observation. And then the history now is the history of the observations rather than the full state action history. Of course, we can turn this into the previous example by just making the observation function equal to producing the whole state action history. So, and then the agents, again, their joint action is put together, and then the joint action is what determines the actual reward. So even though the agents themselves might not be able to see all of the other agents' actions, it's important for the environment to have access to all this information, because the reward function will, we can't calculate what the reward is unless we do know the entire, joint action and the whole, exactly what the state is. This will either be handled by a simulator, or hopefully mathematically we've represented this as like in a real life environment. We hope, the real life environment is, physically calculating and providing this information to the agents based on, like the full state action information. But same thing with the termination condition. So the observation, like there's different ways of thinking about the observation function. You could have this horizon effect where each agent only sees part of the state space. That's what's being shown here. And it also can't see the actions that are being taken outside of its horizon. But there's other ways of constructing this. And actually there is this, if I should make, this thing about belief states. There is this other note, which really, it comes up more in this Sutton and Barto book. But notice how, like in this book, if you look at the subjects, we don't actually cover this partially observable case in here, but there is a reason for that. And one of the reasons for it is that when we talk about approximate solution methods, right, these are cases where we use a function. If I can get an example here, a function with parameters to learn, like here's an example of this simple random walk example. We have this approximation function. And the way the approximation function is structured, um, like the way when you have an approximation function, you have to construct a feature vector, which takes the state and it converts the state into some set of information that is then used by the function approximator. Now, here, the information has been compressed because while there might be this full set of states, the approximation function here can only see which region of the state space you're in, right? It can't actually see that you're in this state or this state. It can just see that you're in this block of states. Now, it turns out that doing reinforcement learning with approximation is equivalent to having this partially observable case. And we can define what is partially observable by how the function approximation is constructed. So you don't necessarily have to think of this as like limiting the state. I mean, whatever information is limited about the state, like what's being shown here, this sort of limitation would not occur in this formal way of like the observation function, but we could actually handle this in the feature vector construction that we have. But then you can look at the case of solving these problems in the case of approximation, which has a bunch of issues that come up with it. And it ends up being like a new problem setting, but it's one where we can combine the study of the approximate solution methods with the partial observability, and it ends up really being an equivalent problem. So here, this is designed so that even in a tabular problem where we're not using function approximation, we can still have this, limited information. But, we could also treat this as a very simple case of function approximation where we just limit the state information by, what information we give to the approximation function. Now there is this discussion in the book about belief states where when we have observations, the agent can sort of try to construct what it thinks the full environment state is based on the action history of the other agents. This uses it can use Bayesian inference. It becomes really intractable. I mean, there's just a brief note here in the book, but they basically say that for complex problems, this becomes a really intractable problem and it's not really dwelled on anymore. And there are some alternatives to this, like we can use some sort of deep neural network to try to update our belief about the state information rather than this formal Bayesian update, which might not be very practical to use. Communication also is, again, there's just some brief notes here about we could use a finite set of messages, and then in terms of a communication action, the agent could just decide, which message to send. In a more general case, it would have to decide what's in the message, and having a policy function that writes an arbitrary message has its own challenges. So, I mean, you could imagine it's really like to write a generic message, you may even want like a large language model inside of this that is then tasked with generating an appropriate message, which of course is something you could do. I'm sure it's in the direction of a lot of current research, but it does introduce a lot of complexity to the problem. Yeah, and then this we'll see later on in the book how much we actually deal with this issue of communication. In this case, also, the action of the agent will depend on not only the history, the observation history, but also the message history, which will be wrapped up in with the observations. Right, which is what's dealt with here, right? The observation function will now need to also consider the history of messages and adjust it somehow. But an example here is you could model incomplete or noisy communication by having the observation function take the message history and add random noise to the history to approximate what it would be like if agents are trying to communicate over a channel where they can't do that perfectly. Um, what else? Okay, we're just about done with all this. Sorry, the remaining information here is a little more game theory discussion. Um, but we should maybe just skip to, yeah, like usually the reason why we go to this partially observable framework is that we want the ability to solve these problems where the agents might have limited information about all kinds of stuff about the environment, about the behavior of other agents, and then we can treat as a subset of that cases where there is perfect information, which is what's done. But typically, in a lot of game theory problems, we assume perfect knowledge of the environment. Here, we're going to hopefully be able to handle cases where there is also limited information, not just complete information. But finally, there's this, if anyone here is more familiar with game theory, there is this little glossary, which is just comparing the terminology. So this book, and how we will discuss this topic is we will use the reinforcement learning terminology where we talk about agents and rewards and policies, right, rather than players, utilities, and strategies. But I guess you could save this page as a little a reminder of how the terminology works. But yeah, I mean, the environment here is not just it's the game, but it's like all of the different games that exist within the environment where when you transition to a new state, you have a new game definition. Or in the case of a non-stochastic game where the game it's just a repeated game, there would only be a single game as part of the environment. Okay, so that's all right. Let me see if I have any other notes in here. Yeah. Well, I mean, the book goes into more detail about why we care more about cases where, we have limited information, because those are usually the interesting problems where, agents, things that are cooperating can't necessarily see in real time all of the relevant information. And we want them to be robust to gaps in that information as well. But we basically want to know, like, what is the best an agent can do if it does have limited information? Like, that's a very relevant case for real world problems. We got this. Okay. So I have one more thing I could show, which is something left over from the Sutton and Barto material. But first, are there any questions about the material, like the stuff in chapter 3, or how we define these games? Again, it's just an introduction to how these games are defined. We won't get into the solution techniques until chapter 4, which I guess we'll begin on chapter 4 for the next meeting. Yeah, but any other questions from people? Or is there any slide or part of the book you want me to go back over? Uh, I'm just going to touch very briefly, just to wrap things up, on this example that was mentioned in Sutton and Barto, which is, if let's consider a game of tic-tac-toe. Now we can design this as a 2-agent zero-sum game, right? In the parlance of this multi-agent learning. But, in the context of single agent reinforcement learning, what we typically talk about is like, so to treat this, um, so to treat this problem as a single agent problem, what we would do, we have this like tic-tac-toe problem here where we alternate. Yeah, so here is like a case of O winning, but to make this a single agent problem, what we would do is fix the opponent, right? And then we would consider learning optimal behavior for the remaining like player. So like we could say we could have the O player and then the X player is part of the environment. And now that we've fixed one of the agents, this now becomes a single agent reinforcement learning problem, assuming, the other player is not also learning and changing over time. Right. So then the combination of the rules of tic-tac-toe and the other player forms the environment. Right. And then what you can do is use these solution techniques where, like what's being shown here, I have to actually fix something here where this solution is not working right. But we can use like these tabular techniques like value iteration to solve this problem. And we can see here, like, so here, this is like learning an optimal policy for X against a random O player. And then you can also do the same O versus random X. And then what you can do to sort of think of this as a multi-agent problem is say, okay, what if we repeat this learning process where now we keep repeating the learning against the opponents that we previously learned, right? So we can say, okay, now we have this version of the X player, which is optimized against the random O player. And then we can say, well, now let's train, like the O player, or like, yeah, I mean, this is just different versions of training, but where now I'm training the O player against that new X player, and then I train the X player against the new O player. And you repeat this process, over and over. And you can end up with here what I'm just showing is different policies and how they've differed over time from the previous policy. But this is like if we take the X versus the random player and compare it to the X versus now the next iteration where this O player has then adapted to the X. Now, with ordinary reinforcement learning, we have, if we fix the opponent, we can come up with an optimal policy for one opponent. Now, once we engage in this back and forth, we're now in sort of a new category where we don't know exactly what will happen. Will this process even converge? What will it converge to? And those types of questions are what you have to go to more look at techniques from game theory to figure out. It turns out if you just have a zero-sum game like this and you repeat this, it should converge to the Nash equilibrium or one of the Nash equilibriums. It's not necessarily unique, but the Nash equilibrium is like if you look at the prisoner's dilemma, it is simply a solution where neither player can make a change to its policy that will give it an advantage. So if you repeat this, where we keep optimizing each player against its fixed opponent, if that process converges, it means that the fixed policy we have for X, if we try to optimize it again, it won't change, which means that the O player has a policy where the X player cannot change its policy in any way to improve that. Now, we don't actually know if this process will find that equilibrium. Like that's one of the open questions we have is, will this back and forth process even find the equilibrium successfully? And then if there's more than one equilibrium, which one will it reach? Also, if we care about both agents competing against each other, it should be obvious that we can't treat it as a single agent problem, right? Like this is a zero-sum game. So let's say both agents just play randomly. Then the sum of the reward for both agents is just zero. Let's say both agents play optimally. It's the same thing. So from the perspective of a central controller that's like reaching a solution, it wouldn't care what the solution is because from its perspective, the reward accumulated over the games being played would never change. It would always be zero. So when you have this sort of competitive scenario, you can only address it with some multi-agent framework. Now, we can easily use single agent techniques and go back and forth and solve this. That's one way of looking at this problem. And it may in fact work, but what it doesn't tell us are the answers to all those questions I brought up. Like, what are we actually solving? What equilibrium are we reaching? What is the goal here? So we may in fact stumble upon like a Nash equilibrium solution that we like, but the point of going through all the material in this book is really having a better understanding of how these algorithms are expected to work. Yeah. So yeah, in Sutton and Barto also, yeah. I mean, luckily with the value iteration solution, we don't actually need this to be a zero sum game for this to work, right? Just like the prisoner's dilemma, right, is not a zero sum game, but you can still find these equilibriums. Same with the tic tac toe. We can, even without the zero sum game, I think a game of this structure will also have a similarly solvable equilibrium. But yeah, I mean, you can also make it so the draw condition is different for one player and the other, which would also make it a non-zero sum game. But let's see. I think so. I don't know. I just wanted to touch on that because we had discussed these sort of competitive examples in the Sutton and Barto book, but we had to sort of stop it at the case of like training back and forth may result in a successful solution, but we don't really understand why that is. For that, we really have to go to game theory. So, any other remaining questions about this or where we're going with the material? So the thing we had looked at is chapters 1 and 3, and then the next meeting where we really get into it will be chapter 4 here, where we talk about really like chapter 4 is a lot more game theory concepts.
Yeah, I mentioned the fact that the Sutton Barter tic-tac-toe game is non-zero sum because I think it makes it a non-trivial game compared to the original tic-tac-toe, which is much more trivial. And I made some tests for the Sutton Barter tic-tac-toe, and it looks like reasonable learning algorithms converge to a situation where both players win half of the games on average, and there are virtually no draws, which is an interesting observation.
Oh yeah. So there could be, I don't know which algorithm you used to reach that solution, but yeah, it is true that depending on the learning algorithm you use, you will end up in different equilibrium conditions. And one equilibrium could be a case where both players draw every game, but there are other equilibriums where they learn some, what's the word I'm looking for? But this case where they're both winning or losing half the time, which is again an equal. I mean, I mentioned earlier that if both players just stick to the random policy, they would also win and lose half the time, and that is not a stable solution because obviously one of the players could start changing their policy to exploit that. And I guess there might be then an actual equilibrium solution where both players win and lose half the time. And I imagine that would be a case where each player is sort of exchanging game states where they're like, okay, for this set of games, I'll let you win. And for this set of games, it'll be reserved for me winning. And then there would be some sort of truce agreed upon where it's like, if you make this starting move, I'll agree to move in a way where you win, but then you have to do the same for me with a different set of starting moves. So yeah, there could be different win conditions. And then you could repeat the test. But I guess, Victor, do you remember how exactly did you train the pair of agents in the case where you're saying it got like that kind of weird solution?
Well, so there was a temporal difference algorithm which was described in the book itself. And in one of the exercises, it asked about a better algorithm. And for a better algorithm, I implemented a version of this with upper confidence bounds for the learning of the.
I know, but
Um,
my question is like, were you learning against a fixed agent and alternating back and forth, or were you having both agents learn simultaneously?
yeah, both
The learning.
agents learn simultaneously.
Okay, yeah. So that will, in general, could produce a different solution than if you do, like, if you train each agent to convergence against an opponent, then each individual learning process will be like a well-defined reinforcement learning problem, which is like there will be a unique optimal policy or optimal value function for that. And then that's another way of handling the problem where you right like you keep one of the agents completely fixed while the other one is learning. That's one version of self play. You can also do right self play where you alternate. And also you mentioned you use like temporal difference learning, and I assume you're doing it with sampling, right? Like it's a stochastic learning process, right? Where
Mhm.
you're collecting samples from the other agent's behavior and then you're doing averaging.
Well, there is a series of episodes. So the algorithm is described in the book. There is no
Oh,
sampling
sure.
other than
Yeah, I just mean which algorithm do you mean? Like you mean like
like
you
it's
mean
the
like
first chapter of the book. Like,
sure. I mean, yeah, but the first chapter of the book doesn't actually have an algorithm. It just has basic.
uh, I think it does.
Well, this is the temporal difference value function update, but this is not an algorithm. Like this algorithm would be
Well, sure, but you apply the value function update and pick a state with the.
I understand, but like these, like the temporal difference update, when you use it with sampling, would be a Sarsa algorithm, like this,
Sure, yeah.
which I assume is maybe what you were doing, some kind of Sarsa algorithm, because you can also do TD prediction with this, where you're just learning the state value function. But when you do this, right, this is you would use to just learn a value function without actually solving the control problem, right, with an actual policy. Like to turn it into a policy control problem, you would use Sarsa, where you're actually learning the Q values, not the state values. But yeah, where they're learning somewhat. So I'm not sure which one you did. If you did it with state values, then that's a little bit different because that actually requires using the full distribution of the opponent's outcomes versus just case of sampling. But I mean, this would be the most common way to use TD sampling with a control problem.
Okay, I don't actually remember the details. I can double check and write
Okay, no,
later.
it's just like there's different. I mean, yeah, like the book does describe a way of approaching this in chapter 1, but again, there are a lot of details missing. Like, yes, there is this like temporal difference update rule, but like the reality is there's like a bunch of different ways to use this temporal difference update, and on top of that, in the tic-tac-toe problem, because it is a simple tabular problem, we can actually solve this problem with a dynamic programming instead, which the example I was showing was a value iteration, right? But this is a case, and there's a way of writing down a value iteration algorithm with multiple agents if the problem is a certain type, which you can do with tic-tac-toe. But if you do this as value iteration, I believe this depends on information later in the book, but you should arrive at the minimax solution for this if it's formulated as a zero-sum game. If it's not a zero-sum game, the solution might be different, but I would guess with the value iteration approach, there are potentially multiple equilibrium states you could end up in. And one of them certainly is the minimax solution that should apply even if the rewards are not zero sum.
But it's not stable, right? Because the agent has no reason to prefer draw over a loss because they have exactly equal reward.
Oh, you're talking about, okay. Well, that's it. That doesn't depend on zero sum or not. Like you could have a non-zero sum game that treats draws and losses differently. Right. It could be like a reward of 1 for a win,
but
0
specific...
for, yeah. No, okay, fine. Now I understand. You're talking about a case where draws and it's indifferent to draws and losses, right? Yeah, that will create a very different. Yeah, that will create a very different solution as well. Is that really what they mentioned about draws and losses?
Yeah, I think for the value TD, we know what state we end up after every single action. So we just need the value in this particular case.
Well, yeah, that's true. But if you want to find a policy, I mean, you do need to act. Yes, you can reconstruct the action values from if it's a deterministic environment. Yeah. But yes, if draws and losses are counted as equal, obviously you'll end up with all kinds of different solutions. You'll end up with a solution that is indifferent to draws and losses, which is very different. I was talking about a case where the game is not zero sum. What was I showing here? So like the way I've constructed this game, let me see where I actually define this. But I believe I did it where yeah, okay. I think I did make it where it is zero sum perhaps, but I am treating draws and losses differently. But you could also, like, if you constructed the game where a win was 1, a loss was 0, and a draw was 0.5, that would not be a zero sum game, right? But it should still have the same solution properties as the zero sum version. Perhaps there'd be some differences. But
well, constant sum is the same as zero sum, right?
Yes, I believe so. Yeah, yes, I think constant sum is the same. And typically, yeah, with this kind of game, with the win-loss draw conditions, I mean, you could also make it not a constant sum game. Oh no, sorry. Where I think it would still be a constant sum game, even if the draw, if you made draws worse for the X player than the O player, yeah, like there might be a way where it's not a constant sum game. But yes, I believe that the solution you found would probably be the same solution you would find with a different technique. Yeah, if you treat draws and losses equally. But really, the main point of thinking about this problem in the context of single agent RL is the idea that if you fix an opponent, and the opponent could be anything, like their policy could be anything in the entire space of policies, then you can actually solve for the optimal policy against that fixed opponent, right? And that's something that you can't do when you think about like minimax solutions where they're assuming that both players are playing with optimal policies. So that's one of the advantages in RL compared to these other techniques. Now we're talking about multi-agent learning. We're kind of going back to the case where we do want to learn this joint solution between both players. But, so you mentioned like there's a TD approach where both agents learn simultaneously. You can also do the RL approach where you fix each opponent and then optimize against it each time and then repeat that until convergence. And if the game is structured in a certain way, that should reach some equilibrium condition. Yeah, but there's games. In the case where the draws and losses are equal, then there might be more than one equilibrium condition. Yeah, there probably is. The value function might be unique, but there'll be a whole I mean, this is true of tic-tac-toe anyway, because there's like, if you look at an optimal policy, even when you do tabular learning, like there could be lots of like equally good actions, right? Even in the single agent case, where we don't actually distinguish, like, right, here's a case where I'm just showing it here where all of these colored actions are like equally good. But there's a whole family of optimal policies, but the value function is equal. Yeah, this is showing. But yeah, so we'll get into more of that next time in chapter 4. We talk about different equilibrium conditions. But yeah, it is interesting to see how the policies evolve over time when you apply different learning algorithms. And even like different discount rates. Like this is treated as an undiscounted game where we don't care, like we don't, it's always going to end in a finite number of steps, so we don't have to discount it. But if you do consider the game with discounting, and different sorts of random opponents, you can wind up with different solutions as well, where a policy could try to win more quickly in exchange for some small risk of losing the game. And those are all different policies you get by just how you set up the problem differently. Yeah. Any other questions or thoughts before we wrap up? Okay. Has anyone actually read this through this book before? Like, and has gone through the different chapters or has looked at any of the summer course material? I'm just like, I've sort of skimmed through the whole book, but I really only read the first 3 chapters in more detail. Okay. Well, I guess it'll be sort of a new adventure for everyone. But we'll see. If you want to prepare for the next meeting, just start reading chapter 4. I guess there are no exercises really to look at, but yeah, you can think about at least the different examples and get familiar with the terminology.